Ah, for the good old days. Wasn't that a beautiful Model T? And then again, wasn't that a beautiful BMW? It all depends on your point of view. One thing is for certain, the old cars were easy to repair. Well, things have changed. Added conveniences and government regulations, anti-skid and airbags, four-wheel drive and four-wheel steering, even environmental temperature control. The method? Electronics, computers, the little black box.
The Corporate Training Department of Standard Motor Products presents this video training program as part of our continuing effort to keep you up to date on how to repair today's cars and remain profitable. This Standard Motor Products Electronic Engine Controls training module covers the Mazda Electronic Engine Control System. In order to confidently and profitably repair these systems, the mechanic must have certain hand tools and some simple test equipment like a volt-ohm meter and a logic probe. Also, he should have a working knowledge of the basics of electronic engine controls and have an understanding of engine computer control systems. He should also be familiar with the concepts of open loop and closed loop, and most important, he should be familiar with electrical and electronic diagnostic procedures.
By now, I'm sure you're wondering, where is this program going? What will I learn? I don't work on import cars. Well, you're not alone. Most mechanics would say they don't work on import cars. But what is a Ford probe? Who makes the Chevy Nova? It's probably safe to say that aside from factory dealers or import specialists, most mechanics do not feel comfortable with what they know about import cars. So as you follow along with this video program, we will supply the information needed to profitably repair Mazda electronic engine control systems. Ready?
The Mazda system, you will see, can be as easy to repair as the average Ford or Chevrolet. Late model Mazdas are equipped with an onboard diagnostic system to assist you in troubleshooting. Before we begin working on the Mazda system, what is the system trying to accomplish? What does each of the components do? How do they interact with each other to affect the operation of the vehicle? Well, the main objective of this system is to allow the vehicle to give good fuel mileage and clean emission, but not at the sacrifice of good acceleration and smooth operation. Mazda's computer control system has been used extensively through their model lineup for a number of years. You should note that the information and procedures outlined in this program can be directly applied to the Ford probe. It uses the same basic 2.2-liter engine as the Mazda 626 and MX-6 vehicles, and also to the Mercury Tracer, which uses the 323 engine. Let's begin by reviewing the operation and function of the engine control system. Then we will look at the system's components and how they relate to each other and the engine control computer. The central or main controlling unit is the engine control computer. The computer takes input data from sensors that monitor various engine and environmental functions. The computer responds with signal outputs to various control devices. The computer controls three primary areas. 1. The ignition system. 2. The fuel control system. And 3. The emission control system. The computer monitors the system input sensors and itself continuously as long as the vehicle is operating. But the computer only checks the output control devices once, during a 3-second period each time the ignition system is turned on and the self-test system is triggered. This triggering is done by grounding the test connector in all vehicles. If a failure in an input sensor is detected during the self-test, the computer will substitute a pre-programmed value. Vehicle operation will technically then be switched to a limp-in or fail-safe mode. Operations during the fail-safe mode or limp-in mode are limited in scope and drivability can be quite poor, but the vehicle will move. No substitution is performed by the computer for output devices. The engine computer is located under the dashboard, on the transmission hump behind the console. The diagnostics display is the check engine light on 1988 and newer models. There is none on older vehicles. This light can be utilized on certain models along with the onboard diagnostic system in the central computer to display trouble codes. It can also be used to check certain switches like the clutch switch and the brake switch. In vehicles that do not use the check engine light, additional handheld test equipment like this simple logic probe must be utilized to access the codes. Logic probes can be purchased from consumer electronics stores like Radio Shack. Also, the OEM sells a test box. Let's take a closer look. The engine control computer receives sensor input readings from the ignitions distributor for RPM and crank angle, an airflow meter signal, water temperature sensor signals, one for engine temperature, one for radiator temperature, an air intake temperature sensor, the oxygen sensor, a barometric pressure sensor, throttle position sensor, a knock sensor on turbo applications, an idle position switch, an EGR position sensor, and a series of miscellaneous switches that can include air conditioning, automatic transmission, power steering, gear shift, etc. The computer uses these input signals and processes them with pre-programmed information. It then responds with signal outputs to control the idle speed, control the electronic fuel injection system, exhaust gas recirculation, the evaporative emission control system, the shift indicator control system, fuel pressure control solenoid, the check engine light for self-diagnostics, and the ignition timing function. A quick review of Mazda's electronic gas injection system, EGI, shows that it has an air filter assembly and ductwork, a Bosch-style vane airflow meter, the meter contains an inlet air temperature sensor, a throttle position switch is mounted on the throttle body assembly, and air plenum. The system has an electric fuel pump mounted inside the fuel tank. The pump contains a drain check valve. It feeds fuel to an inline filter. The pump control switch is mounted inside the vane airflow assembly. The fuel flows from the filter into the fuel rail through a fuel pressure damper. Each individual injector is supplied fuel from the pressure rail. Pressure is maintained by the fuel pressure regulator mounted on the end of the fuel rail. The control pressure is a function of a spring and a vacuum signal. Excess fuel not used by the injectors then flows back to the fuel tank. Mazda does not use the cold start injector system on any of the cars with electric gas injection. The computer's sensor inputs control the fuel injection system in two basic modes of operation. You should all be familiar with the words open loop and closed loop. In a Mazda, they don't work any differently than any other vehicle. The system operates in open loop below a certain temperature and under certain driving conditions. The vehicle's operation in closed loop is used to derive the most beneficial effect of the emission control system in all other modes of operation. In open loop, the fuel injection pulse width is controlled by the computer and the computer program itself without any input from the engine's oxygen sensor or a feedback information system. In closed loop operation, the computer uses basic input signals to the computer from the engine's distributor, giving an RPM and/or cylinder position signal, the airflow meter, and the inlet air temperature sensor, which together supply a signal on the mass of the incoming air, the throttle position sensor and idle switch signaling the demand on the engine, and the exhaust gas oxygen sensor signaling the outcome of the combustion process. These inputs operating together determine the fuel injector's pulse width to help minimize emission and increase drivability. The emission control system contains no surprises. A conventional evaporative system, EEC, is designed to trap fuel fumes in a charcoal canister. Two solenoid valves control canister purge. The solenoids receive their signals from the engine control computer. The computer uses input information from the airflow meter and water temperature sensors. The EGR system is also fairly conventional in layout. In this MX6, or the Ford probe, the EGR function is controlled by the computer. The computer uses primary input information from the throttle valve sensor, engine coolant temperature signal, and the radiator water temperature signal, an RPM signal from the distributor, and a transmission signal. The computer makes a decision and sends a signal to the EGR solenoid valve, which controls the vacuum available to the EGR modulator valve. The vacuum modulator assists in controlling vacuum to the EGR valve. Other components of the emission control system include a PCV valve system, a deceleration fuel control system, and a catalyst system. The third system, controlled by the engine computer, is the ignition system. Depending on the engine style and the year, the timing function can be controlled either by centrifugal advance, vacuum advance, or an electronic spark advance, ESA. Electronic spark advance is found on the 2.2-liter turbocharged engine on the MX6 and Ford probe, also in turbo engines used on the 323. All turbo applications use a NOx sensor to retard timing. The computer controls timing by processing signals from the airflow meter, the idle switch, the clutch or neutral switch, the EGR position sensor, a NOx sensor, throttle sensor, water temperature sensor and water thermo switch, an inhibitor switch, and the electronic control automatic transmission control unit. The computer controlling signal is used by the ignition igniter assembly. The igniter assembly, or ignition module, controls the primary current flow through the ignition coil. This control of the coil's primary current flow controls the ignition spark advance. Mazda also utilizes the concept of HEI, high energy ignition, on many of their ignitions. As you know, this is merely a function of the output voltage available from the ignition coil. A very conventional appearing secondary system is utilized for wires, cap, and rotor. The individual components utilized by Mazda throughout their electronic engine control and fuel injection system should be familiar, as they are not any different than any other brands. The electronic engine control and electronic gas injection, EGI, system has been used by Mazda since 1986 on the 323 and 626 models. Many of the sensors utilized in the 323, MX6, 626, and Ford probe are also utilized for the RX-7. In fact, the engine control system is similar. We will not make any attempt to perform diagnostics or repair functions on an RX-7 during this program. Additional information on the electronic engine control system as it relates to the fuel injection system can be found by viewing the high-grade fuel systems training videotape entitled Mazda Electronic Fuel Injection.
That's it. We have covered the basic components and functions of Mazda electronic engine control systems. Now, to repair some common problems. Hands-on experience may be the best teacher, but through the use of video, we can simulate everything except your hands actually touching the components. Ready to begin?
This Mazda is similar to all 323 and 626 electronic engine control systems since 1986. The owner of this MX6 has called and requested you pick up the vehicle with a wrecker. The complaint is a no-start condition. Upon questioning the customer, you find that over the past few weeks, the vehicle has been repeatedly difficult to start. But on previous occasions, after repeated attempts, the vehicle would run. With the car in the shop, what is the first step? What do we look for? Even though you don't work on Mazdas very often, and in fact you much prefer working on domestic cars, you are willing to give it a try. As you follow along with this program, you will see that it is not any harder to repair this Mazda than a domestic car. The first thing we need to do is to follow a logical approach to troubleshooting. Ask the customer for some general information, especially about the exact year and model of the vehicle. The engine style is very important. Then, ask the customer the questions necessary to determine exactly what the complaints are and the history on the vehicle. Remember, you cannot diagnose a problem that does not exist. Keep in mind that the self-diagnostic system in this vehicle cannot troubleshoot everything. There are certain things that should be checked visually or with some simple test equipment, like a volt-ohm meter or a logic probe, before beginning to work on the computer itself. Considering a no-start situation, or at least an intermittent one, we should first check the ability of the starting system to turn the engine over. Check the battery leads, the cranking system. Remember to always check the obvious. Check the primary and secondary ignition systems in the normal manner. Always check the antifreeze and coolant level. Remember, the computer must have an accurate temperature sensor reading to compute the proper air-fuel mixture to run the engine. A no-start situation. It could be fuel, and it could be ignition. Since it is obvious by turning the key that the engine turns over, the first step would be to determine whether a fuel problem exists or an ignition problem exists. Since this program is designed to deal primarily with the engine control system as it relates to ignition and emission control, we will follow the electrical-related branch of a trouble tree. Any problems related to a fuel system will not be covered here. The easiest method to troubleshoot this vehicle is to utilize the onboard diagnostic system first and eliminate those problems with trouble code readouts. Even though Mazda says that you should purchase or utilize their proprietary diagnostic equipment, it is a simple matter to derive trouble codes utilizing a logic probe on all models since 1986. On 1988 and newer vehicles, it is possible to utilize the check engine light on the dashboard. On 1986 and 87 323 and 626 models, the self-test connector is found adjacent to the engine control computer on the transmission hump. After moving the carpeting out of the way, or moving the computer itself, follow the wiring harness from the computer towards the engine compartment and locate the 6-pin connector and the single green connector. Pull them free of the harness wires to gain access to the plugs. If you are utilizing Mazda test equipment, simply plug the 6-pin connector into the self-diagnostics checker on the 323 and turn on the ignition switch. If you are testing a 626 or a 626 turbo, you must also ground the Mazda diagnostics checker. Remember, the Mazda computer system only checks the output devices when the system test connector is grounded and the ignition switch is turned on. If you did not ground the test connector, only input devices will read trouble codes. If you are working on a 1988 or newer 323, Mercury Tracer, Ford Probe, 626, or MX6, the 6-pin green plug will be found in the engine compartment near the master cylinder. Besides the Mazda tester, you may also utilize a simple logic probe to test for codes. A logic probe is a solid-state electronics test device that will read the trouble code computer information string and also give an audio buzzer signal of the trouble code string triggered by the computer's diagnostic circuit. First step in hooking up the probe is to connect the black and red leads of the logic probe to a power source. Next, insert the needle probe of the logic tester into the appropriate pin on the 6-pin connector. Turn on the ignition switch and read trouble codes. If you want to check output devices, ground the single lead from the harness assembly. If you have a 1988 or newer vehicle and will be using the dash check engine indicator, simply turn on the ignition switch and ground the single lead connector. This will trigger self-diagnostics utilizing the dashboard light. Since we are working on a 1988 MX6, which is also identical to the Ford Probe, we could utilize the dashboard indicator light, but we will also hook up the logic probe to illustrate the connection. With the equipment hooked up and the logic probe powered, turn on the ignition switch. Note any codes for future reference. Remember, codes vary by year and model of the car. On, off, on, off. A 01. This indicates a problem with the ignition pulse or no ignition signal. That makes sense, since the vehicle will not start. First, check the ignition coil, both primary and secondary. Specifications for the primary coil winding for a non-turbo are 1.04 to 1.27 ohms. Now, check the secondary. This looks like a simple epoxy coil, like the E-coil found on GM vehicles. On a non-turbo vehicle, we are looking for between 7,000 and 10,000 ohms. Check the high tension lead for continuity. Remove the distributor cap and check the rotor and cap for carbon tracking. With these tests completed and the problem still not located, proceed with the next step. Do a resistance check on the igniter pickup coil. It should read between 900 and 1200 ohms. This is also within specification. Next, consulting a schematic illustrates that the power feed to the ignition coil from the battery travels through the engine main relay. The relay supplies power to both the ignition coil and the injectors. The schematic illustrates that the engine control computer switches the ground side of the ignition coil to complete the primary winding's current flow in order to fire the coil. Obviously, the trigger is the igniter module input from the magnetic pickup. That has already checked OK. Do a power check with a high-impedance digital volt-ohm meter at the negative terminal of the ignition coil. With the key on, there should be battery voltage in both crank and run position. If no power is present, check the engine main relay. Since we have power present, the next test point is at the computer itself. Mazda does manufacture a proprietary test box not unlike a Ford breakout box, which connects between the engine computer and the harness. This breakout box will supply both current and voltage readings on each pin position. But utilizing a high-impedance digital volt-ohm meter or a logic probe, it is possible and permissible to determine if battery voltage is available on pin 1M of the engine computer. With the ignition key on, battery voltage should be present on 1M. Crank the engine. It should still have battery voltage available. Since we have 12 volts at pin 1M, we are close to the problem. Check the power to the computer from the ignition switch, terminal 3B of the computer. 12 volts is available with the key on and in the start position. Based on these findings, it will be necessary to replace the engine control computer. With the computer replaced, start the engine and allow it to come to operating temperature. Next, make sure all the electrical loads are off, including the air conditioner. Connect the timing light and verify initial timing. Connect a jumper wire between this green test connector and ground located adjacent to the distributor. Now, recheck the idle speed. It should be approximately 750 RPM. Recheck the ignition timing with the test connector grounded. On this non-turbo engine, it should be approximately 6 degrees with the vacuum hoses disconnected and plugged. With the timing and idle both reset, road test the vehicle before returning it to the owner. If the complaint had been traced to a component other than the actual computer, any component where a trouble code other than 01 is displayed, it would be necessary to clear trouble codes after the vehicle has been repaired. Mazda's procedure for clearing trouble codes states that after repairing a failure, turn off the ignition switch and disconnect the negative battery cable. Depress the brake pedal for at least 5 seconds to erase the memory of any malfunction code. Then, reconnect the negative battery cable. The number of codes varies between the 323 and the 626. 1986, 87, and 88 model vehicles have additional trouble codes added to each year. Unlike the other manufacturers, Mazda also makes it somewhat difficult to read the trouble codes. As you can see from this illustration, a 0-1 is a simple on-off pulse. An 8 and a 9 are simple pulse counts of 8 or 9. A 10 is not 10 pulses, as you can see by both this diagram and the sound of a buzzer indicating a 10. 1 pulse, long pause. 1 pulse, long pause. A 12, 14, 15, and 17 are one long on pulse, followed by 2, 4, 5, or 7 short on pulses, followed by a very long pause. 25, 26, 28, 2 on pulses, followed by sequential short pulses of 5, 6, and 8. It may at first appear difficult to understand their pulse codes, but after working with them for a short period of time, they will become familiar. Utilizing the proper service literature, common sense, and some basic knowledge of electronic engine control systems, you will find Mazda's as easy to repair as any domestic vehicle. Remember, don't turn away that Ford Probe, Mercury Tracer, or 626 the next time it comes into your shop.
This concludes working on Mazda electronic engine controls. As you have seen, they are not difficult to troubleshoot and repair utilizing onboard diagnostic systems. I would like to take this opportunity on behalf of Standard Motor Products and its corporate training department to thank you for purchasing this video, and we hope you will consider us for your future replacement parts needs.
Control head is connected to an electronic servo motor. The electronic servo motor uses the basic sensor input readings, the in-car sensor, the ambient sensor, the driver's control panel, and matches these resistance combinations to position the blend air door to the proper position. As the driver moves the control lever to a cooler reading, lowering the resistance at the control head, the servo motor reacts by moving the blend air door to a cooler position or lower resistance. The in-vehicle temperature sensor functioning with its aspirator assembly is nothing more than a thermistor that converts its temperature to an electrical resistance value. A change in this resistance affects the amount of current flow through the servo motor, altering the position of the blend air door. The ambient sensor also works as part of this network in the same manner. Remember, the operator must manually change the blower speed in this system. Now let's take a look at Chrysler's EATC system, Electronic Automatic Temperature Control. It is found on front-wheel drive vehicles like this Chrysler New Yorker or Dodge Dynasty. In this system, a computer totally controls the blower speed, airflow, recirculate or fresh air, hot or cool to maintain the desired set temperature. The computer is an integral component of the dash control panel. This system also contains a self-test or diagnostic circuit in the computer. It will read out fault codes to help troubleshooting. A PVM, Power Vacuum Module, is positioned on the blend air door housing. The PVM powers the compressor clutch and blower motor. It also controls vacuum to the heater water valve and certain vacuum motors. The blend air door is controlled by a DC motor wired into a feedback circuit. As the door is moved, it sends a feedback signal to the computer, telling the memory circuit where it is, for example, 15 degrees or 20 degrees, etc. Let's test this Chrysler New Yorker EATC system and repair any problems found. First, conduct a performance check. Start the engine and let it reach operating temperature. Press the panel button on the AC control. Make sure the display lights. With the display lighted, press the defrost, floor, and bi-level buttons at the same time to enter self-diagnostics mode. Note, as of 1988, this button is labeled Auto. You should see all the elements on the display at this time. This is your clue that you have entered the self-diagnostics mode and the system testing is in progress. The whole test will take about 90 seconds. With a notepad in hand, let's watch for trouble codes. A code 14. No other codes are indicated. Before any repair work is started, press Off. If the system were tested and it found no fault codes, a 75 would read on the control panel. The trouble code 14 indicates a problem with the ambient temperature sensor. So let's continue and remove the sensor and check the component. With the glove box panel removed from the dash panel, it is not a difficult task to unscrew and remove the ambient sensor from the air plenum. With the unit unplugged, measure the resistance of the sensor. It should be 3,000 to 40,000 ohms at between 30 degrees and 120 degrees Fahrenheit. This is a very wide range, but normally the component will open circuit when it malfunctions. We have an open circuit, identifying a failed component. With the component replaced, again, do a performance check of the ATC system. Then recheck the self-diagnostic system and look for fault codes. Note that testing and repair of the in-car sensor is done in a similar manner. You can see that most problems can be corrected with the use of a simple volt-ohm meter and service literature and the self-diagnostics procedures outlined.
This concludes working on automatic temperature controls. As you have seen, they are not difficult to troubleshoot and repair utilizing onboard diagnostics. I would like to take this opportunity on behalf of Standard Motor Products and its training department to thank you for purchasing this video, and we hope you will consider us for your future replacement parts needs.